What deadline did I give for the design homework? Okay, that was a stupid thing to do, I guess, obviously. Okay, well, uh, okay, you guys are lucky. You'll obviously uh, you get to hear my great lecture. But in any case, firstly, a bunch of announcements which sort of went out on Piazza, but I'm sure you were tied up with doing the design assignment. So a problem set is out, design assignment is out, and there's no lecture on Monday. We'll have a makeup for that on the 5th. I'll send out the details. That's Thursday of the following week. And also my office hours next week are kind of shifted, all of them. So just take a look at the... okay, so any questions? The design assignment kind of builds upon the current one. So this time around, you have to make a sequential system where there's a kind of two nodes, if you may, two devices. One which is the Morse code transmitter, the other is Morse code receiver. And just like in kind of real systems, what happens is they are remote, and that usually there is kind of a single channel on which you send out bits one at a time, so in a serial fashion. So that's what happens in this particular assignment. So you'll have to design a sequential system around the Morse code coder and decoder that we have built in this assignment. So that's kind of the way it is structured, and you'll have to design finite state machines, kind of stuff that Paul and Salma have talked about in the discussion sections and also in the lecture. The problem set is all on sequential systems. It's sequential stuff is a lot harder than combinational, so I would really urge you not to kind of leave it to the very end, because it's trickier, just as homeworks go. That's the first thing. Another thing is I've given lots of problems because I just wanted to get comfortable with it. So there are many problems to get you to practice, because it's sort of newer stuff than before. So it's a longer homework, I guess. When are getting our midterms back? Actually, where are we on that one? Okay, probably Friday. Yeah, we have the solution ready, so I'll probably send that around. But one change that we did do, just to kind of announce that, is there was a problem where I think this was problem number 4B, which is where you had to find codes which were appropriate. So I had given an example of an error code with 2 bits error, and then I asked for that, what if we are sending pairs of bits? And what we kind of realized was that was something that was probably a bit of an unfair question, in the sense that you had to search for an answer. There was no kind of very systematic methodological approach. So what we did is that we decided to remove it from the base midterm and make it an extra credit problem. Okay, so in effect, what happens is that we'll sort of score the midterm out of, after excluding that problem, curve everything along that, and then if you attempted that problem and did something, then that would be extra credit. So the way the grading will work, just to without taking into account your extra credit score, will first grade, okay, and then your extra credit stuff gets tapped on, and if you move to a different grade band as a result, then that's what will happen. So that's how things will work out. Okay, so back to state machines. We saw state machines the past couple of lectures and also in the discussion section. And again, kind of to summarize, and before kind of recapping some of the stuff that Paul and Salma kind of talked about in the discussion section. So state machine, we kind of think of them as bunch of states. States you can think of as bunch of distinct histories. Okay, so the status of the system, where each state corresponds to something distinctive about the past. So that's what we have as the set of states. We also have an input alphabet. So the way to think about it is, I have a bunch of input lines coming in, and at every clock I'm looking at them. So you can think of an n-bit line to define a set of 2 to the power n possible input values. So that's kind of like a set of possible inputs, and that's the sigma. So it's the input distinct input symbols that we can see. Likewise, there is a set of output symbols. So if I have a 1-bit line, then my output symbols are just 0 and 1. If I have two 1-bit lines, then 0, 0, 0, 1, 1, 0, 1, 1. There are 4 symbols, and so on and so forth. There is a state, which is the initial state, which is where we go upon power up. And then there is a set of transition functions, which basically say, if I am in a particular state and I observe a particular input, then what is the next state? Okay, so it defines the rules of transition. And then finally, there is an output function, which basically says, in each state, given a particular input, what is the output? Okay, and if we ignore the input, that is, in any state, if in all the state all the outputs depend only on the state that we are in, then that's the Milli machine, otherwise it's the Moore machine. So we saw that in many ways. Now when it comes to designing these things, so kind of as you might imagine, kind of the basic idea is that you come up with this state diagram that we've been seeing. From that, we make that state transition table, state and output transition table, so which is essentially like a glorified truth table, which captures the two combinational logic functions that we have in our system, the next state function and the output function. And then you make those combinational logic functions using Carnot maps and all, okay? There's one other piece which is missing in it. When we draw the state diagram, we just draw these nodes, and they have some conceptual meaning, but then you also need to decide how many bits you are going to use to represent those states. So let's say in my state machine I end up having 10 states. Then of course I need at least 4 bits, but I could use more bits. I could encode these 10 states in a bunch of different ways, much like what we saw earlier in the class, that if I have some distinct pieces of information, I can use a variety of different ways of encoding them. So the overall flow then looks like you're usually given some specification for the problem, and in the PSET as well as the design assignment, you have plenty of examples of that. And the first thing is to come up with the strategy, like any system design, software or hardware, and that's obviously purely a manual process. Then you make the state diagram usually corresponding to it. So instead of diving straight to hardware, you first think of it at a higher level. So you make a state diagram, and this FISM tool that we have been talking about kind of assists in that process. Then you assign state actual bit values to those states. Okay, so you kind of say, how do I map these states to specific bit vectors? So in my example of 10 states, if I decided that I'm going to do one hot coding, then that means each state is represented by a 10-bit vector, and therefore I'll need 10 flip-flops to represent all the states. I could have also decided to do a fully encoded state. So I could have said, okay, only 4 bits, and I'm going to use some 10 of those 16 combinations, and that would be another state assignment. And there are many other possibilities. And then at that stage, we have enough information to fully work out both the next state logic and the output logic. We'll see an example of that manual one. So you kind of go through that process, or you can use tools. So FISM outputs code, Verilog code. Verilog is a hardware description language. Then that code you can simulate. So kind of the idea is that Verilog code, without even going all the way down to gates and all, you can just simulate that Verilog code and find bugs in your state machine. So it's kind of a higher level simulation. Then that Verilog code can be taken by a synthesis tool. Yosys is the one which we have introduced to you. And what it does is you run it, and it gives as an output a netlist of gates. Okay, so that's your implementation. And in commercial strength tools, that netlist of gates, you can kind of then feed it to further tools which kind of lay out, which create the silicon masks for making the chip, or map it to these field programmable gate arrays. In our case, you'll see the netlist, and then you manually can put it into Logisim. Okay, we do not have that bridge to go from the output of Yosys to Logisim automatically. So that's our implementation. Once you have it in Logisim, you can do another simulation now. Now this time around, you're doing a simulation in terms of gates. And hopefully what you see here should map to that higher level simulation that you would see there. Now, when it comes to this course, you can skip some of these steps. You can just go dump Verilog, don't do simulation, move to Logisim, just do your simulation there. You're familiar with that. Or if you want to play with Verilog level simulation, you can do that. We'll sort of provide some additional details on how to access these tools and all. So in the discussion section, Paul and Salma went through an example where kind of they showed how FISM works, kind of run the output, take the output of FISM into this script, which then gives Verilog. And finally, you have kind of a picture like this, which is netlist. And we'll provide you a library which basically makes the gates that you see to be one which are available in Logisim. Okay, so you will see things like 3-input NAND gates, 2-input OR gates, 2-to-1 multiplexer, things like that. So you could literally kind of just take this and feed it into write it into Logisim. Okay, so that's how the flow works. And that Verilog output that comes out of FISM, like I mentioned, you can simulate. You can simulate that as well, and in which case you can get kind of a timing diagram which looks like this, which kind of also lets you debug your state machine at a higher level. So as you are doing the problem set, I think you might find it useful, because some of these things are tricky, to do it in FISM so that you can do this kind of simulation and verify that your design is correct. Okay, because otherwise there might be cases you might miss. So essentially at that stage it becomes once you have the Verilog, it becomes a testing problem. You feed inputs to it, see whether the output makes sense, test out different scenarios. And again, this Friday, the Paul and Salma are going to go over that. The other thing we have been doing is this traffic light controller example, which again, sort of I worked on it the last time around, and Paul and Salma did. So I'm not going to go through the state machine again, but rather walk you through how the manual design process looks like. So this state machine, as sort of then corresponds to the problem specification. So we have 4 states corresponding to 4 distinct possible configurations of the 6 traffic lights. And then there is a sensor input called car east-west. There is also a reset input, and then we kind of move back and forth. It's very common in sequential systems to have an input called a reset input, and I'll talk about it a little bit later on. But the idea is that since we have flip-flops, and we want flip-flops to not go into an arbitrary state. So let's take an example. Let's say I decided I have these 4 states, so I need at least 2 bits. But I could also choose to implement it as one hot code, for example. So I can take 4 bits to represent each state. 4 bits can represent 16 distinct possible state values, of which only 4 are valid for our system, the ones which are the one hot code. What if our system, upon power up, the flip-flops come up in a state which is not a valid one hot code, in which case the system will go berserk. So the idea is that by having a special reset signal, we want to make sure that our system goes to a specific known state and not to the flip-flops do not get initialized to a random value and then sort of operate totally randomly after that. So reset signals are often seen. Sometimes you would draw them explicitly, sometimes they're implied. So it's kind of implied that whenever the reset signal comes, we'll go to the initial state, okay, which is marked somehow specially. Okay, so in FISM it gets marked with the state with a double circle. So this is our state machine, and we see 2 inputs here, the reset input. So it's, as you can see, if I have reset in any of the states, I always come back out here. And otherwise, every signal, every transition is marked with that there is no reset, basically. So like I go from GNS to YNS only if there is no reset. The numbers that you see out here are basically listing the values of the 6 outputs that we have, the 6 signals controlling the 6 traffic lights. So I can design them in FISM and all, but the question then becomes, how could I do these things manually? What happens under the hood? So first thing, faced with a transition diagram, and what I have done now is I've removed the reset signal. Okay, so you can always imagine that if reset happens, I always go back to state number 1, but we have just ignored reset. Okay, so that's taken care of separately by the hardware. That's a very common approach. So you focus on all the other signals. So this is our state machine without the reset signals. And the first thing you do is you make this state transition table, or oftentimes I refer to as state transition table and output table. So because really two tables. And what we see out here is the following. What we see out here is if I'm in a current state, then what the next state is and what the output is. Now, if you look at this machine, it's a Moore machine. You can see that the outputs in each state are constant. They do not depend upon the car east-west signal. So I can say, given the current state, I can always talk about what the output is, and that's what we are seeing out here. So the 4 possible values of current state and the corresponding 4 outputs that we have. And see how I have kept the states here still in a symbolic form. Okay, I have not told you what bits correspond to the state. We'll do that later. The other thing is, what is the next state? Now, next state does depend upon the input. You can see that I have a couple of transitions out here which depend upon the car east-west signal. So what we do is we say next state, and I have 2 possibilities for the input. Car east-west is false and car east-west is true. And depending upon that, the next state takes different values. Okay, so you can see if I'm in the state YNS, then independent of what car east-west is, I always go to the state GEW, which is the second row. If I'm in the state GNS, if car east-west is false, I stay in GNS. If it is true, I go to YNS, which is these 2 transitions. So what we see in this table is exactly what we have in the state diagram. But the idea is you kind of start with the state diagram, and in a manual approach, from the state diagram, you draw a table like this. Okay, at which point you have still not assigned. We know there are 4 states. We'll have to map them to some bits, but we don't know what the bit pattern would be. There are many possibilities to do that. Infinitely many possibilities. Any question on this? Okay, so next thing that comes up is now we need to actually assign specific bit representations for those symbolic states. So our states were, I have these 4 states for whom all I have are names. I need to assign some values to them, and that would dictate how many bits I would have in my state register. How many flip-flops do I need? So that will decide the value of S for us. Okay, so one approach is a so-called one-hot state assignment, and it turns out that for manual design it's very easy to do. The negative of that is that it needs more flip-flops. Okay, so in our case I have 4 states, so I need I'll assign 4 bits, and I'll encode GNS as 100, YNS as 0100, GEW as 0010, and 0001. So the other 12 combinations should never occur. So, and that's why we need the reset signal. So when we start out, flip-flops come up in a random state. Usually the power-up circuit generates a reset pulse, and that will force the flip-flop to go to my initial state, which I think in this example we assume to be 1000. Okay, so this is our encoding. So now we can go back to our table, and wherever we had GNS, we plug in 1000, wherever I had YNS, the corresponding value, and so on and so forth. So at that stage, I have a concrete realization of the system. And then the question becomes, so imagine I replace these things, and now basically I have a truth table where I have 5 bits of input, 4 for current state and 1 for car east-west, and I have 5 bits of 10 bits of output, 4 bits of next state and 6 bits of output. So I have a combinational module which takes 5 inputs, so 4 bits of current state and 1 bit of car east-west, and it outputs 6 bits of output for the lights and 4 bits for the next state. So it's, at that stage, it's a combinational logic problem. You can kind of solve it and be done with it using techniques we learned earlier in the course. But there is also, once you decide that I'm going to do a one-hot coding, there's almost like a one-to-one translation you can do from the state machine out here, and I want to walk you through that. Okay, and let's do the following. Let's just jump to get rid of the animation. Okay, so the idea out here is the following. Remember, it's one hot code. So I need as many flip-flops as the number of states. And when I'm in state GNS, there will be a corresponding flip-flop which would have the value 1, or the other flip-flops would have the value 0. And likewise for YNS and GEW and YEW. So see how I have drawn 4 flip-flops underneath each one of the state. So whenever I'm in state GNS, this flip-flop will have 1, all the other 3 will have 0. Whenever I'm in YNS, the second flip-flop will have the value 1, all the other 3 will have 0, and so forth. Then comes the question, what can I do about the transitions? So let's start with, let's say I'm in GEW. So the third flip-flop is 1. And the question is now, what happens in the next clock tick? Well, as this guy shows, in the next clock tick, I always go to YEW. So what will happen is I will have, in one clock tick, I would have 0, 0, 1, 0. In the next clock tick, I want 0, 0, 0, 1. So the 1 has to move from this third flip-flop to the next flip-flop. And the easiest way to do it is just wire it up. So the 1 in this third flip-flop will move to the fourth flip-flop. The 0 in the fourth flip-flop will move, has to move back out here, and so forth. So we just have to shift everything. Is that point clear? That if I connect 2 flip-flops back to back, then the 1 which is out here moves to the next one, and in parallel, the 0 out here moves out here, and so forth. Okay, so that's the basic structure, but then what about our transitions? So this is where sort of we come out here and say, okay, let's look at GNS. Under what conditions would GNS be 1? So GNS, the flip-flop for GNS will be 1 if either I was previously in the YEW state, or I was already in the GNS state and car east-west was false, right? Those are the 2 possibilities how I can continue to be in GNS, right? So GNS would be 1 if YEW was 1, or GNS was 1 but car east-west was 0. And that's what this little logic up here does, okay? It's basically, if you look at it, it is ORing the output of YEW flip-flop with car east-west complement ANDed with the output of the GNS flip-flop itself. Likewise, YNS. When would I go to YNS? Well, I'll go to YNS if previous state was GNS and car east-west was true. So that's what you see out here. You see there's an AND gate out here, and it is ANDing GNS and car east-west, and that's what we are feeding out here. GEW, we are going to go to GEW if previously we were in YNS. So that's a straight wire. And we already discussed about YEW to GEW. So state transitions just map to some simple piece of logic sitting in front of at the D input, and otherwise you essentially kind of wiring things up straight. So anytime I have a state going straight, I just put a straight wire. Anytime I have some conditions, we map it to logic. And this you can literally, you should be just able to kind of write it down by just looking at the state diagram. So one hot coding makes that comfortable. Now other part is we need to provide the outputs. Now the output part is also reasonably straightforward, because if you look at it, you basically say, okay, let's look at the first output, the green, let's see, yeah, green for the north-south. So that's the very first bit. Well, this output is going to be high when I'm in the state GNS, and that's it. In all the other states is 0. So that's why the green out here is tied straight away to the flip-flop out here. Let's look at something perhaps more interesting. Let's look at the red for the north-south. So you see out here how it's a 1 in GW and a 1 in YEW. So what you see, this red guy is actually getting, did I mess things up out here? It's an ORing. So yellow corresponds to I am in state YNS, so that's what we are getting out here. Red corresponds to I am so red is high, this guy is high when I am in one of these two states. So another way of saying it is low when I am one of these two states, and that is what this logic is doing, this NOR gate out here. And finally, green for east-west is high when I am in GEW state. So that's what you see. The green out here is wired up to the GEW. So let me kind of write down on the flip-flop so that it kind of becomes a little bit more clear. So this is the flip-flop for GNS. This is the flip-flop for YNS. This is the flip-flop for GEW. And this is the flip-flop for YEW. And so for each one of these output signal, I basically have to kind of form the right combinational logic so that it is driven out here. So main thing out here is you can just put down a flip-flop for each one of the state and literally just traverse through every transition and work out for each one of the output, and you'll get this logic. So in the problem set, I ask you to do a couple of problems in this particular fashion. So you should get comfortable with it, because in an exam-like setting, this is the simplest thing I can ask, okay, one hot coded, okay? So you should be very comfortable with taking state machine and in a one hot code fashion, give me an implementation for it. It's inefficient because the flip-flops are there. A single flip-flop is worth several gates, okay? Flip-flop is probably worth around maybe 8 to 10 NAND gates, okay? So it's a costly thing. So every time we are using unnecessary flip-flops, it is adding to the area cost. On the other hand, it's very simple to kind of make this circuit. Questions? Okay, looks like everyone is very comfortable with this. Okay, so the logism realization that Paul and Salma showed to you. The other approach is that we think of some other code. So one possibility is that I have only 4 states. I make them only 2 bits, and then furthermore I do what is called as gray coding. Anyone remembers what gray code is? Anyone? Yeah. Okay, you do. Anyone else? Gray code. What is that?
Every consecutive
yeah. So every consecutive thing differs by 1 bit only. So you go from 00 to 01, 1 bit difference. 01 to 11, 1 bit changes. 11 to 10, 1 bit changes. 10 back to 00, 1 bit changes. Okay, so successive numbers are changing only by 1 bit. Or on the other hand, our regular binary code, like as you go from 0 to 15, let's say, there are cases where multiple bits change. Okay, so gray code has the advantage only 1 bit changes. It results in some nice electrical properties. So anyway, for whatever reason, we decided to pick that out here. So this is our coding. So GNS maps to 00, YNS maps to 01, GEW maps to 11, YEW maps to 10. And then we can plug them back into our table, and this is the truth table that we will have now. So see how the state values I have plugged in. And now I basically have to implement the stuff, which we use Carnot maps. So I'm not going to walk through the Carnot maps, but using the methods that we have done before, you kind of create the Carnot maps, you come up with the equations. So I have now in this particular case, how many outputs do I have in this combinational function? Even? How many total outputs would I have in this? 8, yeah. So 6 original output and 2 bits of next state. So I am designing 8 combinational functions, right? That's one way of 8 combinational functions where the number of inputs is 3, right? 2 bits of state and 1 bit of Kari space. Well, more precisely, for 2 of the outputs, I have 3 inputs, and for 6 of the outputs, I have only 2 inputs. Okay, so I can kind of design these. So again, Carnot map, you build up these things. These are all the logic equations which sort of you come up with, and then you map it into a circuit. Okay, I did this manually into Logisim, which is how it kind of looks like out here. So unfortunately, with the kind of tools we are using, we do not have the automated way of kind of doing it, as I mentioned, but at least again with circuits with few states, this is not that bad a process. In FISM, when you're designing, you can actually tell for each state when it is outputting Verilog, you can tell it what kind of coding to use. So you can tell it use one hot coding or use this highly encoded way of doing things. Or you can even manually assign the things. You can say for this state, use this code. For some other state, use some other code. So with whatever rationale that kind of drives you. So that's kind of the manual process. So again, to summarize, start with state machine, make that state output transition table with symbolic names for the states, then decide a bit pattern to give to each one of the states, and then either straight away or by just looking at it or using the one hot code trick or Carnot maps or any other tool, you basically come up with a logic implementation, and then you wire up the flip-flop. So if you look at my design out here, what you see out here is that the output of the next state logic feeds into the D inputs of my two flip-flop, and the output logic drives the 6 LEDs which correspond to our traffic light. Okay, so that's kind of the process that one has to go through. Now, I want to give another example and kind of highlight some of the issues as you design these state machines that you are likely going to face, or very common mistakes that come up. So let's take another example. This is a timer for a laser gun. Okay, so the kind of stuff where play at ultrazone or even kind of other laser guns that you can imagine. So the basic idea out here is that the specification is this thing has a button as the input, there's a clock, there is an output X which fires the laser. And what we want to do is whenever we push the button, fire the laser for 3 clock cycles. Okay. If button pressed while laser is already firing, you ignore the thing. So this is an example. Clock signals coming in, input, B goes high. When B goes high, if you see that at the clock edge, it recognizes that B has gone high. So out here, at this clock edge, it noticed B is high, and then it does on for 3 clock cycles. Okay, and then it goes back to 0. So if you look at the output, this is how it's going to look like. Looking at this, can you tell me, is this a mealy machine or a Moore machine? Just from the timing diagram. So don't look on the right hand side. Okay, I know. Just from the timing diagram, would you be able to tell me whether it's mealy or Moore? How about you? Huh? You're not quite sure. Okay. Someone else at the back? How about you in the blue shirt? Hello? Hello? I'm asking you. Yeah. Okay. Well, you want to go short? Okay. It's more. Why do you say it's more?
One is low, it's off, and like the output is the same as there are 2 states for the output, 2 states for the input.
Okay.
It's low, the states low.
Okay. So another way of thinking about it is the following. Remember, in mealy machine, the input immediately has an effect, right? So what one would have expected out here if it was mealy is whenever B went high, it would have fired. But it's actually waiting until the next clock cycle. So that's kind of a giveaway. Now, I had mentioned before that faced with any problem, you can always do it with mealy or Moore. Okay. The key thing to remember though is that Moore machines are slower in reacting. They cannot observe the input until the effect of input cannot happen until a clock edge arrives, right? Whereas in mealy, it can react immediately. Now that makes mealy machines more agile, lower latency, but also the problem is that if there was a, like for example, if for whatever reason, some electrical noise or something, B had a little bit of a spike, your gun will fire. Okay, not a good idea. So mealy machines tend to be less robust, but they tend to be faster in reacting. So one good thing to one good practice is that when you are faced with a problem where you have to design a state machine, think in terms of what is happening in time. Kind of draw some simple timing diagram just to get the feel of what is happening, and also what are the tricky cases. Okay, this is a simple problem, but like for example, that UCLA problem that I had a couple of lectures ago, it had some tricky transitions and all happening. So make sure that you cover various test cases. Then once you have a good feel for it, then you can move on to kind of making the state diagram. So in this particular case, the idea is I am in an off state, and while I'm in the off state, and looking at the state diagram, you can see it is immediately more because all the outputs are part of the state at a constant. So when I'm in the off state, it is 0, so laser is not firing. When the B input comes, I move to on 1, the laser is firing, then I unconditionally move to the next and unconditionally move to the second one. So on 1, on 2, on 3 are my 3 states where the laser is firing, and then I go back. And this little thing out here is telling that off is my start state, and if B is not firing, I stay put in this state. Okay, so that's kind of the basic structure that we have for the state machine. Now, so looking at this again, I can convert it back into that mathematical description. What is my set of states? Well, I have 4 states, set of input, 1 input, set of output, 1 output, initial state of the transitions. In our particular case, there are 5 transitions, and then there is a set of actions, the outputs that we have to do. In this particular case, is some more machine. And then you can translate that into okay. Now, common mistakes when you are making these state diagrams, or things to remember, okay, as you do it. So the first thing to remember is that for all transitions leaving a state, only one condition should be true. So it should never be the case that you're in a state and your transition conditions allow you to take, you give you a choice that, oh, I can take this transition or that transition. That should never happen. Okay, what it means is that the conditions on the transitions should be mutually exclusive. So like for example, in this case, I should not have 2 edges going out of the off state, both of whom are saying take that transition if B is high. That will not make sense. So that only one condition should be true. There, in theory, there is a class of state machines which allow for a choice. They are called non-deterministic finite state automata. They are usually studied in or described in computer science theory classes, but real hardware is deterministic unless you are into some quantum computing type stuff. Okay, so it is deterministic. So one transition has there should not be a choice. The other thing is that it should never be the case that if I were to so another way of saying that they are mutually exclusive is that if I take any 2 transitions with any 2 edges and I were to AND their condition, they should always be false. It should never be the case that both are true simultaneously. Okay, next problem. Let's okay. For all transitions leaving a state, one condition must be true. Okay, so this is the dual of that. So here I said it should never be the case that more than one transition's condition is true. Here we are saying, but one transition must be true. Okay, even if it's a loopback. So it must be the case that for every state, for every possible input values, I have an answer as to what the next state is. I cannot leave that undefined because then again, the hardware will not know what to do. So for all transitions leaving a state, a condition must be true. Otherwise, the next state is unknown. Now, sometimes even tools like FISM, they basically say, if you do not specify it, then I'm going to stay put in that state. So as far as this course is concerned, for you to get complete credit for your state machines, you have to explicitly list every transition. Okay, so that's a good habit because otherwise you have a mistake in the sense that did you forget the edge or were you truly very smart and are relying on that default value? And I would rather that you specify fully out here. So what this means is that if I were to OR all the conditions for outgoing edges, then they must add up to 1. Okay, basically saying one of them must be true. Now, let's look at another, so how these things play out. So let's say I have a structure like this in the state machine. I have a node, I have a transition saying A, which is going to the top state, and I have a transition going B, which is going to the small state. And looking at this, you may say, okay, this looks fine. The problem with this is I have not told you what happens if A and B are both 1, right? If A is 1 and B is 1, then I have a choice. So therefore, there is a problem out here. So one way to fix it, you can say, if A go here, if not A but B, you come down out here. Now the problem with this is, what if A is 0 and B is 0? Then both of them are false, and then again I'm not specifying anything. What would you do? So you see the problem. So it started out with what looked like a reasonable structure, but it had the problem that A and B could be simultaneously 1, and therefore I will not know which transition to take. So in an attempt to fix it, what I did was I added this if. So if A go top, if not A but B, come out here. But that still leaves another condition unspecified. What am I doing if not A? If A is 0 and B is 0? Now, one answer is, okay, it's implied that you stay put, but alternatively, a better answer is that you actually add a self loop, and there you say not A, not B, you stay put out here. So the thing I want to emphasize is, in this course, I want you to adopt this kind of practice. There is nothing implied. If you give me the solution like that, it will be marked wrong. Okay, so very important to fully kind of specify this. So let's see how these things kind of play out in kind of an example. So I'm sure you would have seen some of these locks which have sort of a keypad to kind of open them up and all. So what we have is a lock like that. So what this lock does is it basically takes inputs S, R, G, B, and A. So there are 4 buttons, and the idea which basically go high when a button is pressed, and then additionally there is another signal called A which indicates some button is pressed. And then I have an output U which opens the lock. So the idea is that there's a code detector out here, and whenever that code is met, the lock is sent a signal to unlock. So main thing is we want to unlock only when buttons are pressed in a specified sequence. So in particular, we want to open the lock when the user presses start, followed by red, blue, green, red. That's what we want to press. So the code is hit start, press red, blue, green, red in that order. Anything else, the lock has to remain unlocked. So you can think of it like, it's like our UCLA problem, right? I mean, we want to basically detect a pattern out here. And with the additional thing that if a wrong button is pressed anytime, go back to the initial state. Okay, so the lock basically kind of, anytime we have the wrong code, go back to initial state. So this is what we have out here, the state machine. So let's walk through the state machine. We start out in a state out here, initial state, and we're basically saying S prime, you stay put out here. Okay, so basically saying if no button is pressed, I remain in start state. If start is not pressed, you remain out here. If start is pressed, we move to the next state, and I still am outputting 0 on the output. If A is not pressed, we stay out here. If there no button is pressed, namely A is false, we stay put out here. If a button is pressed, so if A is high and R is 0, so it's a wrong code, we go back to initial state. Otherwise, we move to the state called red. In the state called red, so we are basically saying I have seen S, I have seen R. Now out here what we do is, again, if no button is pressed, we stay out here. If a button is pressed and it is blue, I move to the next state. If a button is pressed and it's not blue, I go back to the beginning state. And then in the blue state, I do the same thing. If green is pressed, I move here. Otherwise, I go back out here. If R is pressed, I move out here. Otherwise, go back out here. Okay. Question: can you fool this lock? I see one hand raised. Okay. Yeah. Can you be a little more clear on that? You press all the buttons at the same time. Okay, that will fool this lock. Okay, can anyone tell me why would that happen? Someone from this side. So the suggestion out here is that, okay, I'm going to again impose on you. Can you tell me now what's happening? No. Okay, if you're going to be in the lecture, then pay attention. Otherwise, you don't need to be here. Lectures are optional. Okay, so please pay attention. Okay, it kind of is annoying as a teacher when I see someone just going off. Okay, so anyone wants to explain why this is happening? So he's right. I press all the buttons and the lock will open. Okay, so my code doesn't work. So could you see now if I press all the buttons, what's going to happen? So let's say I'm in the wait state. The user has pressed all the 4 buttons, S, R, G, B. Okay? Follow now.
Will you have the start press goes to the next one, and then a button pressed as well as the red, so it'll go to the red. The button pressed, so
It will just, successive clock cycle, it will just keep going out here. Okay? And the lock will unlock. How can you fix it? Oh, okay.
You have to make a state for every single possible combination.
Right. So what would you do? So let's think about it. I want to go out here, but do not want to run into this problem that the user is fooling me by pressing everything. So you go out here only if other keys are not pressed, right? You have to add those conditions out here. So, and the same logic will kind of hold true in every place. So this is kind of what it starts looking like. So we attempted to modify it. We basically said, okay, I'm in this state. If it's not R, or if it is B or G, I kind of go back, and so on and so forth in each one of these things. So I kind of add this other condition to prevent that from happening. Okay, so prevent this simultaneous thing. Are there any other problems with this? Right. So again, what we have done is we have sort of specified. So let's look at this one. So we're basically saying if a button is pressed and it's red, move out here. If a button is pressed and it's not red, or it is blue or green, kind of move back out there. And same thing with others. So problems with this?
Easy to figure out, so it doesn't go through a whole cycle of 5 buttons. So if you push.
Yeah. Okay. I think. Yeah. So you are proposing a weakness in a lock like this because it tells me immediately that, oh, I'm starting on the wrong thing. So okay, that's a poorly designed lock. Okay, but let's. You're right. Okay. So your system should not tell me my password is wrong right after the first character. It should wait until I have typed all the characters and then it should tell me I'm wrong. Right. Okay. You're right, but that's not what I'm looking for. State machine part of things. So look at the following transition. So consider transition of state to red one, from start state to red one, and then back to wait. Okay, so what's happening is that this particular transition, this particular transition, start to red one and to the wait. If I look at these two, okay, there are 3 outgoing. There are, if you look at these two and AND them, it is 0. Okay, so there's a failure which is consequently happening. So if no button is pressed, we stay out here. If a button is pressed and it's red, we go out here. If a button is pressed, then nothing, I go out here. So if a button is pressed, we do want to do some transition, right? Which must happen. So main thing out here is that when I'm taking this particular edge, I cannot simply say that it's A and R. We have to say it's A and a button is pressed and it's red and it is not B and it is not G. Okay, because otherwise, going back to our thing before, that we do want to make sure that these things should not simultaneously be true, right? That is, there should not never be the situation where something is pressed and I have a choice between the two. Okay, so in particular, if I'm in state start and the user pressed blue and red simultaneously, then AR is true and AR prime plus B plus G is true. Okay, so that will violate our requirement that it should never be the case that two transitions are simultaneously true. Okay, so I have to therefore modify this thing, and I don't know whether I have done it or not, but no, okay, I didn't. But the point is that this AR should really be AR B prime G prime, and the same logic will apply everywhere else because it was violating our condition number one, no choice. So basic rule again is that for every you're in a state, look at all possibilities of inputs. And for any input combination, there should be exactly one choice. Okay, it should not be the case that no choice is defined. That nothing is defined, and it should not be the case that you have more than one choice. There should be one and exactly one transition from current state to the other next state, some next state or loop back for a given input pattern. Okay, if not, it is not a valid finite state. It's not a valid deterministic finite state machine. That would be kind of the right term for out here. So these mistakes are very easy to make, particularly in a setting where you are actually not implementing the design. So you're never simulating anything and all. You're just drawing something on a piece of paper, and it's very easy to overlook these kind of issues. Okay, so good practice therefore is to at least kind of conceptually, mentally go in each state and kind of say, does it make sense for every possible input? Do I have a very well defined next state defined for me? Okay. Bringing sequential circuits to a known state. So this is a point we touched upon earlier when I talked about the reset signals. So the issue out here is that when the system starts up, the flip-flops, these are electrical devices, they can come up in any state. So a flip-flop may be on 0 or 1 with equal likelihood. Sometimes flip-flops are designed so that they come up on power up to a given state 0, but oftentimes that's not the case. So they'll come up with some random value. So you power up memories, they have some random content in them. And as I mentioned, that can cause problems, like in an example like this, where only if I was doing one hot coding, then some of the state values are invalid. Like for example, the state 0000 will never occur if I'm doing one hot coding out here. Okay, so what we want to make sure is that right after power up, my state registers are set to an appropriate valid state, in particular whatever is my initial state. So the initial state can be noted by, as we have seen, either by this kind of arrow, start, an arrow going in, or with this kind of a double circle depending upon the syntax being used, or maybe somewhere else said initial state is this. So that's that's one issue. The other reason why we want to go to initial state is something went wrong. Okay, for whatever reason, my system is hung, stuck, cosmic rays hit it, the circuit went berserk, any number of things. So the idea is, in that case, we are usually given a reset button. The computer is frozen, you sort of press some button for 5 seconds and it resets the hardware kind of thing. Oftentimes in systems, they also have something called watchdog timers. So watchdog timers are basically counters. And the idea is in your software, you tell that little piece of hardware that if I do not come back and access you again in the next 10 seconds, you should go ahead and reboot the hardware. So you basically, there is this really foolproof little circuit which we have to keep accessing off frequently. And if the software doesn't access it, then this little circuit sends a reset signal. It reboots the whole hardware. And kind of the idea is, if the software is frozen, then it will fail to access that timer, and then the timer will bring things down. So in many like remote systems, like you're designing some sort of a device which is going to sit in a forest and hard to access and all, what you want to do is, if the system realizes it's hung, it reboots itself. That's kind of the concept. So this ability to bring sequential circuits to a known state is very important. And the way it is done is a very common is to essentially have a signal called a reset signal, and sometime you could say there's a set signal, but the system will have a reset signal. And then the idea is that this reset signal would ensure that the system goes into a known state. So one way of doing it is that you make this reset synchronous. So I will, whenever I want to reboot the reset the system, I will set my reset line to 1 or 0, whichever polarity it is defined with, and then at the next clock edge, the system will reset itself. So you could think of that reset is nothing but a special input feeding into my next state logic. And in the next state logic, what it does is whenever it sees reset is high, then it will output a next state which corresponds to my initial start state. Okay, so for example, I may have something like the following. I may have an AND gate. I can take my reset signal, I can invert it, and this is really an S-bit AND gate really. So whenever reset is high, this output of these AND gates are going to be 0, and my state register is going to be reset to all zeros. And the idea is if all 0 is my start state, this thing works. Okay, if my start state is something else, then you can think of a different circuit out here to make that happen. So reset goes high. At the next clock tick, the state register will take a fixed known value, and this way we are good to go. Actually, it turns out another reason why we have to do this kind of reset also is that some simulators require it. So it turns out, again, simulators don't know how to deal with unknown values, so they represent unknown values by an X, like it's neither 0 nor 1. So you have to initialize your flip-flops in the simulator to a known value. So there are many number of reasons why having a reset is a good idea. So you could do it this particular way. Alternatively, I could even make my flip-flops be like that. So this is what this guy is showing. So imagine my good old D flip-flop, which we have seen before. What we do is in front of it, we put an AND gate. And this AND gate gets a data input, and it also gets a reset n. This means that it's a negative polarity. I want to reset when reset n is 0. So the idea out here is as long as reset n is high, this AND gate has no effect. It behaves like a normal D flip-flop. But if reset n is low, then on the next clock tick, this flip-flop will take on the 0 value, right? Because if reset n is 0, then the output of AND gate would be 0, and therefore at the next clock tick, this guy will take the value 0. So that will reset. So instead of drawing this thing like this again and again, you can imagine a D flip-flop which gives you a reset n signal. And internally, it would be doing something like this. Or it could be a positive reset, in which case it will be just RST, and in that case, there would be an inverter sitting in front of this AND gate. So any bunch of ways you can imagine. Let's say I want to provide a set functionality. So there are also flip-flops which are settable. They will have a signal called set. I raise the set signal, next clock tick, the flip-flop will take on a 1 value. How would you do that? How can you implement a flip-flop which provides me with the set input so that at the next clock tick, the flip-flop will be set to 1? Kind of analogous to this. Any thoughts? So again, next clock tick, I want the output, the flip-flop to become unconditionally 1. Exactly. So OR gate, one input is D, the other input is set. Okay. So that's what we're out here. And you can imagine flip-flops which have both. If anyone played with Logisim flip-flop yet? Looked at it? No? Okay. If you're going to Logisim, look at a flip-flop. It has both set and reset. But the set and reset in Logisim are not synchronous. That is, they do not wait for the next clock edge. They do it immediately. They're kind of like melee inputs. Okay, they set or reset immediately as opposed to waiting until the next clock tick. So that brings me to the next point, which is there are 2 ways of doing set reset. One is at the clock edge, and the other is immediately. At the clock edge is called synchronous, which is what I've shown thus far. It has some good advantages. flip-flop is less complex, circuit is completely clock synchronous, and I'm immune to spikes in my reset line, like the reset line is coming from a switch or something, no glitches and all. But it has some disadvantages too, which I'll sort of not go over. They have to do with kind of the implementation details and all. So what that leads to oftentimes is circuits which have asynchronous reset. And the idea out here is reset happens as soon as the reset signal comes. It doesn't wait for the next clock tick. But to make this work, you need to modify the internal transistor level circuitry of the flip-flop. Okay, so it's trickier. We are not going to discuss in the course. If you are an EE student, you will probably see it in 116C, I think. It's not 116C, 115C, which is a digital circuit class. But asynchronous resets are pretty useful. And if you look into the D flip-flop in Logisim, you would see that it has asynchronous reset. I've just copied from the manual, asynchronous reset, which is located at the southeast end. So this little bit out here is asynchronous reset, and it also has an asynchronous set, which is this bit out here. The D flip-flop in Logisim also has an enable signal, so this enable signal, and the idea out here is that if enable signal is 0, then clock is ignored. So it's as if the flip-flop is no longer operational. So let me ask you a following question. Okay, so go ahead.
Sort of an implementation issue. So how would you create an asynchronous D flip-flop?
A D flip-flop with an asynchronous reset?
Yeah.
So come and talk to me after class. The reason is because it requires some analog level circuitry inside the flip-flop. So it's no longer a digital circuit. It's no longer a clean digital circuit. Okay, or let me rephrase it. Okay, hand wavy. Remember we saw the SR latch very early on in class. Okay, so essentially you put a SR latch inside the D flip-flop, and that has an effect, because if you recall, the SR latch had that property that the moment I asserted S or R, its effect was going in. But the thing it had was it had gates which were in a feedback loop. Okay, so it kind of gives a weird kind of a behavior. Question I wanted to ask you guys is slightly different. Look at this enable signal. This enable signal is saying when this is 0, clock triggers are ignored. Otherwise, and so the current bit continues to appear in the. So let's try to design that. So this is what I want to do. I want to have a D flip-flop which has an enable signal. Now remember, the normal D flip-flop, what it does is, whenever the clock tick comes, whatever is on D gets captured by the flip-flop. So normally, okay, this is a normal D flip-flop, but I want a D flip-flop with enable, and what it says is if enable is true and clock has an edge, then Q equal to D, else Q equal to Q previous. This is the behavior we want, that I want to consider clock edges only if enable is high. Can anyone think of a way of using our traditional D flip-flop without the enable to give me a D flip-flop which has this kind of behavior? A mux. How would you do it?
So you have a mux, so it's like 2 to 1 mux. And then the control signal is by enable.
Excellent.
And then 0 is controlled by Q and then 1 is controlled by Q.
Good. So this is what he's suggesting, and it's right on. Okay. Consider this circuit. Okay, and what I have done is, if enable is high, fill is low. If enable is low, the upper path of the mux is active, and therefore clock edges are coming, that's fine, except whatever is the value of Q is what I'm feeding back out here. But if enable is high, the lower path is activated and then D feeds into the flip-flop, and that gives me this behavior. So this suddenly gives me a flip-flop which I can load on demand, right? I can basically make it read D whenever enable is asserted, okay, whenever enable is high, and otherwise it just holds its value, the clock ticks can keep coming. So I'm no longer stuck with that every clock tick the flip-flop updates. I can control its behavior. So selective enabling of the writing of the flip-flop. So very useful. Generally speaking, these kind of behaviors of flip-flops or other kind of flip-flops and all, you can always make them by putting some appropriate logic in the front, and you just have to kind of ponder about it a little bit. Okay, so as you can see, by we made a flip-flop with a synchronous reset a little bit earlier somewhere, right? This guy. We made a flip-flop now which has this enable signal and other such properties you can make. A cautionary note: you will see flip-flops which they will say it has set and reset. You should always read the manual to figure out whether it's synchronous set or reset or is it asynchronous set or reset, because they are both labeled the same way, just called S or R. So very important. So if you look at the symbol in Logisim, it doesn't look any different than something which was in my slides a short while ago. It has a input called reset, but only when you read the manual do you realize that the Logisim flip-flop has a asynchronous reset. And it does bring me to kind of an important point, what I kind of something I've tried to say on Piazza. It's very important to kind of understand some of these behaviors of modules and the tools in Logisim, because otherwise you may accidentally make mistake. You may make assumptions which are untrue. That's one part. The flip side is you may do rather inefficient designs. Okay, so just keep an eye on that. If you look at Logisim, it has many other type of flip-flops also. In particular, and these are something called T flip-flop, something called JK flip-flop, something called SR flip-flop. These are less common, but I'll just list them out here. So toggle flip-flop, as this one is called, so T flip-flop. Its behavior is that if T is 0, then the output retains its value. If T is high, then output is complemented. There's a little complement sign out here. JK flip-flop. So it has two inputs, J and K. And the idea is if J and K are both 0, flip-flop holds its value. Clock ticks can keep coming, the value will not change. If J is 0, K is 1, flip-flop becomes 0, so it's reset. If J is high, K is 0, the flip-flop is set, 1. And if both of them are high, then the flip-flop toggles. Again, there's a little complement sign out here. And then finally SR, whose behavior is listed out here. So these are all flip-flops available to you, but as you can imagine, I can always make all of these guys out of my D flip-flop. So let's talk about it. How can you make a toggle flip-flop out of a D flip-flop? So again, toggle flip-flop's property is it has one input called T. If T is 0, then the flip-flop retains its value. If T is high, the flip-flop toggles. If it was 0, it becomes 1. If it was 1, it becomes 0. How would you make such a flip-flop? Yeah, so XOR with the T. So this is what it would do. Remember, XOR acts as an inverter depending upon what we are feeding to it. So if you look at this circuit, if T is high, so if T is low, then XOR basically disappears. Output of XOR is whatever I'm feeding it back, so it holds its value. If T is high, then it will toggle it, right? And you can similarly implement the other ones. I'll let you figure it out. So really the fundamental flip-flop that we have is D flip-flop. Everything else is convenience, okay? Everything else, synchronous set, reset, enable, all of it can be made with surrounding it with some combinational circuit. So to summarize this part, this particular module, sequential logic, we saw the concept of states. We saw how we can think about sequential systems at many different levels. We can think of them in circuit terms. We can think of them as a state diagram. We can think of them as a state transition table with symbolic names for states. We can think of them as a state transition table where we have actually put bit values for every state. All of these things are dancing around kind of the same concept. The other thing we saw is that we are largely limiting ourselves to synchronous systems. That is, action happens at clock edges and not otherwise. There are sequential systems which are not synchronous. They're much harder to design, so we don't deal with them here. We saw that there are different ways of doing the state assignment. I gave a couple of examples, one hot and just this encoded binary. But literally, I mean, you can many different ways you can map. What do you think might drive my choice? Like when it comes to states and mapping them to bits, what all factors may come into play? What would guide your decision?
So what you're trying to do with them. So if you were to try and say each state had a specific LED you're turning on or something like that, then maybe one hot would make more sense. But then for binary, say each state is a different count of something, then binary might make more sense.
Okay, that's one thing. Sure. Any other reasons? Some which we already covered. So I talked about like cost, like number of bits I need. That affects the number of flip-flops. So that's one reason. Can you think of something else? Under time pressure in your final exam, given a choice, what would you use? One hot code. Okay, remember that. Okay. On the other hand, if you have tools, you let it optimize for area or power or whatever. Okay, so these are kind of different criteria that one can pick. One other thing which I wanted to talk about, and that is Paul and Salma did cover it, but I just wanted to bring that out also. And there is another way at times to think about this system. So remember our problem that I had looked for the pattern UCLA. And then I had made a state machine for that, right? And in the homework, you will actually have a few problems like that also. But there is another way of approaching this problem, which is a quick and dirty way. And imagine this is what I'm doing. So UCLA, I'm getting letters. How many bits I need? Let's say they are coming as 4-bit letters, right? I have 26 letters. I can encode them in 4 bits. So I can imagine a system where I'm getting 4-bit inputs. And what I do is I feed them into a 4-bit flip-flop. This is a D flip-flop, 4 bits. I take the output of this guy, feed to the next one, again 4-bit. I take the output of this guy, feed it to the next one. And I have 4-bit out here. So firstly, tell me, what is the meaning, the output of the first D flip-flop? What does it represent? So my inputs are arriving every clock cycle, a new input. What does the so input represents whatever I have input. What does the output of this first flip-flop represent? The input at the previous clock tick. What does the second one represent? 2 clock ticks ago. What does this guy represent? 3 clock ticks ago. Okay, right? Now let's say my strings were coming in and I got, the user sent me the string A, B, C, U, C, L, A. Okay, so A will come in, will filter through, B will follow through and all. At some point I will have a U. B has already been discarded, it's thrown out. I may see something like this, UCLA, okay? So if I want to detect UCLA, successive clock ticks, what I can do is I can take this guy, take this guy, take this guy, take this guy, feed this thing into a magnitude comparator or whatever, some circuit where I compare this guy against A, I compare this guy against L, I compare this guy against C, I compare this guy against U, I take this guy, take this guy, take this guy, take this guy, feed it into and voila, I have a UCLA detector. Okay. So This works great. Why did I go through all that FSM before? Do you see some disadvantage of this design?
It's a lot of gates.
Okay, but I can probably implement these things much more efficiently than I've shown. It will not be a comparator because I'm comparing against a fixed value. Okay. How many bits of state do I have here? Anyone? How many? Huh? 12, right? I have 3 flip-flops, 4 bits each, 12 bits of state. 12 bits of state, that means I have 2 to the power 12 states, right? Do you recall how many did I have in my state machine? I think it was 4 or 5. So it was like 2 bits or 3 bits, right? Right, 5. Okay, so 3 bits of state. Okay, much more efficient that way. Okay, now let's imagine I were to enhance this thing to say, what if UCLA I'm okay with UCLA in successive clock cycles, but it could also be that maybe they are in alternate clock cycles. So if I allow for that, well, I'll need to introduce more, right? I mean, the problem with this approach is that I have to remember the oldest input that I could depend upon. And that could be long, right? So this may require a lot of history, okay? And therefore very inefficient. On the other hand, for certain problems, like this particular problem, it's seductively easy, okay? I mean, literally, you're not, like everything I've taught, you can ignore and just kind of build this thing up, okay? So useful in some cases. Certainly, I mean, in software, if you were implementing that thing where I were to say, you write a function where every time I call you, I'll give you a new letter, you'll probably implement it this way. You are probably going to have 3 variables representing the 3 older characters you have seen, and then do the comparison. Okay, it's fine there, but when it comes to these gates and all, and you're worrying about individual gates and all, this strategy just blows up on you. Okay, so just wanted to present this one. Questions on this? I think this is the approach which I think Paul had called a state vector approach, right? Yeah. So it's used, it has its place, but it's no substitute for proper full-blown design. Okay. Okay, so let's move on to next thing up. Question?
Oh no.
Okay. So just like in combinational circuits, when we started out, we introduced a general way of making combinational circuits, Karnaugh maps and stuff like that. And then we came up to combinational building blocks. We said, if we had these building blocks, job of making combinational systems became easier. Same thing a little bit with sequential systems also. We could certainly design any sequential system using the methods I have described thus far. The problem is that there are classes of sequential systems which become painfully inefficient doing it this way. Let's take an example. Let's say I tell you design a 32-bit counter. Okay. How many states will a 32-bit counter have? Anyone? A lot. 4 billion. Imagine it's FSM. Okay, 4 billion bubbles, it's not going to work, obviously, right? But more importantly, it is insanely regular, right? I mean, all that is happening is one state to another state to another state to another state, and we are kind of looping back, right? I mean, so clearly, thinking about some types of sequential systems as finite state machines, diagrams, is insanely inefficient, okay? At the same time, these things are routinely used, right? We use counters and all in our systems all over. So the trick again is that these kind of functionalities, these kind of sequential functionalities, we are going to think of them as building blocks. And then we are going to design more complicated sequential systems by just using them as building blocks. Okay, so what that brings us to is the style of designing sequential systems, where we think of our system as having kind of two types of two parts. There's a part which we can think of as dictating the control logic of the system, like how like if this then that kind of thing, okay, where we are thinking about how the logic of my system is kind of branching out or iterating or things like that. And then there is the other part where I'm actually remembering large amount of data or processing large amount of data. Okay, in your computers, if you write a program, there are two types of state which a program has. Okay, one is your variables. Every time you say int x and you put x equal to 3 or whatever, you have just created 32 bits of state. Okay, and when you do arithmetic on that x, you're essentially you are doing some sequential processing. But there is another state in a computer, which is where in the program you are. Anyone knows what that is called? Like when a computer is executing a program, what decides where in the program you are? Program counter. Anyone else heard of it? Program counter, right? It basically says which address am I next going to execute an instruction from, right? That is part of a state also. And then when you say if something go here, otherwise go here, that program counter takes a branch. If you have a for loop or while loop, that program counter goes back, right? So that is part of what is called as the control of the program, the control flow of the program, right? There's not massive amounts of data involved there. It's just that puny little program counter and some conditions and all, but it is affecting how, what pathway am I taking through my code. So that concept has its analog on the hardware side, and these are called data path finite state machines. Okay, so these are sequential systems which have both a control part, think of them like a program, and a data part, think of them as our variables and operations we do on those variables. So let's walk through that. So this module, in effect, we are going to look at sequential systems which have huge amounts of state, which you cannot conceivably capture as a finite state machine. So suppose we want to make this state machine. Okay, this is our counter. So we are basically saying the states go from 0 to 31. If anytime I see a reset signal, I go back to state 0. If I do not have a reset, you just keep counting to the next state and the next state and the next state and roll back. Okay, so this is a 5-bit binary counter which is resettable, right? So any time I send a reset signal, next clock tick, it will go back to 0. So I could certainly design it like this. I could make it state transition diagram, list the states, list the next state logic, and do all of that. But now imagine we want to do a 32-bit one, and as we discussed, it would have 4 billion states. So not very good. So a better way out here is to use a data path type approach that we call as data path like approach. Okay, so what does that mean? Well, kind of the idea is that if we look at this next state of the circuit, of the sequential circuit, what it is saying is next state is equal to reset. Next state is equal to 0 if reset is high. Otherwise, it is state plus 1. Right? If you think about how in a programming language, for example, you were to write it. By the way, this is the good old operator that we saw in the midterm. So next state is if reset is high, then 0. Otherwise, it is state plus 1. Okay, and looking at this, immediately the logic pops out on it. Okay, right? Next state. So what does this structure remind you of? What hardware does this correspond to? Question mark colon. Condition. If condition is true, the first choice. Otherwise, the second choice. Mux, right? So what this is saying is my next state logic has a mux, which is being driven by the reset signal. One input is 0. The other input is the current state plus 1. So it's an adder or an incrementer of some form, right? So I can immediately make the shoot, what did I do? Yeah. So this is an example of what is called a data path, because you can think of this part instead of putting into an FSMNO. I'm going to think of them as I have a variable called state, I have another variable called next state, and I'm doing some arithmetic operations on them or some logic operations on them. So essentially, a data path type sequential system is one where instead of thinking in terms of tables and all, I'm going to think of it in terms of these expressions which map to combinational building block modules like we saw earlier in the course. So by the way, this we already know, so we can skip this part. Okay. So another way of saying is I could actually compact this table to look something like the following. I mean, I'm basically saying if the current state is A, then the next state is A plus 1, if reset is 0, otherwise, and if reset is high, next state is 0. Okay. And I can implement it as we imagined using a mux and this plus 1 circuitry, an incrementer, which is nothing but you can assemble it out of a bunch of half adders, for example. Okay, so straightforward circuitry. So this part that we are seeing, this mux in this, you can think of it as our it's a function, it's a combination logic which is doing the arithmetic operation or the logic operation we have described, and then this is our state register. But if you are coming from a software side, you can say this is our program variable. Okay, this is my int state, and then I have written a code which is saying state is equal to reset question 0 colon state plus 1, right? In C or Java or whatever, that's how I would write it. So this is so I've stopped thinking of it in terms of a state machine and transition diagrams and all. I'm thinking of it in terms of variables and arithmetic operations on them, arithmetic or logic operations on them. This is merely a different way of thinking about the same underlying reality. Okay, it's just that for certain things, this way of thinking is going to be easier, whereas certain other things like our lock example for and all, if you that lock example I had earlier on, if this key is pressed and all, if you think about your program that you would write for it, you would have a lot of if then else or case statement or stuff like that, right? It would have a lot of these control oriented parts of our programming language, whereas if you were to write this is going to be more dominated by arithmetic expressions and all. So this is a simple counter, but which we are viewing differently. The advantage out here is whether I'm designing a 5-bit counter or a 128-bit counter, it looks the same other than n changes, right? I mean, so the complexity of my design doesn't blow up. I mean, it basically, I just add more bits in parallel. So that's nice. So if I look at a more general form of data path circuit, it looks very much like our good old sequential circuits. It's going to have a next state logic, it's going to have an output logic, it's going to have a state register. The difference is you will think about the state register as a variable or a collection of variables. Output logic and next state logic, I'm going to think in terms of expressions. Every clock tick, output gets a value which is computed from these variables, and the next value into these variables is computed in terms of the old variables and perhaps some inputs that are coming in. So if you think of it as this is a method that you are writing, the inputs are arguments to that method. The state is the variables associated with that object or the variables that you all that you have as part of your code that you remember from one run to another. And then output is whatever you are returning. Okay, so if you have done like Java or C++ or that kind of programming language, then you can think of this whole thing as implementing a method for a class where arguments to the method, internal state of the method, return value of the method. Okay, that's the analogy that you can draw on it. So this is, but as you can also see, this looks like our good old sequential circuit, except that I'm no longer making a finite state diagram for it. Okay, so let's take another example. Let's say I want to make an up-down load counter. Okay, so I want to make a counter which can count up, which can count down, and which can be loaded with a value. At any time I can say load this value into the counter, and then from that point on it will count up or down from that value. So this counter, the system would have a count output n bit. It would have a signal called reset, so that I can reset it, bring it back to 0. It will have a signal called up. So if up input is high, the counter counts up. If down input is high, the counter counts down. If the load input is high, what the counter does it reads the value which was on the input state and loads it out here. Okay, so that's the functionality we want. And again, we could have implemented a FSM diagram for it, and for very small values of n, maybe we stand a chance. But once n grows up reasonably modestly, we'll have a problem. But if I were to just express it in expressions, it will look something like that. It will say, if reset, next state is 0. If not reset and up, next state is equal to state plus 1. If not reset and down, next state is state minus 1. If not reset and load, next state is in. Otherwise, next state is equal to state. Okay, so you can just think of it as a bunch of conditional statements that sort of we are doing that we might do if you were to express it in a programming language term. What does this structure remind you again? How would you implement it? Mux again. Usually these things all, anytime you see if bunch of ifs and all, is some sort of a mux type structure that you will end up having. So output function is straightforward. Output function basically says count is equal to state. So the other thing is, in this particular case, we are basically assuming that reset overrides everything, and up, down, and load are guaranteed to be one hot. So that is, only one would be high. So these are part of our specs. I could have created a table, except that my table would have lots of rows, not very good. I could create a symbolic table like this, where I could write in terms of the current values of state. State is q, and I could write q plus 1, q minus 1. This is far more compact, so which is like our expressions. Okay, so this is our circuit going to look like. State register, I will have a 4 to 1 mux now. And what we are doing is the following. Remember, we have reset, up, down, and load. I have 4 signals which affect what my next state is going to be. If reset is high, next state should be 0. If up is high, next state should be current state plus 1. If down is high, it should be next state should be current state minus 1. And if load is high, it should be in. So what we have done out here is created this 4:1 mux. If you see out here, and by the way, if all are low, then we retain the value. Now, instead of making a 5:1 mux, what we did is we created a 4:1 mux and then have a separate incremental decrementer out here. Excuse me. So what you see out here is one input of the mux takes the current value back. So that is my current state. That's the top input. The second input is the input coming from the outside world, what we want to load. Third input is the current state plus 1 or minus 1, and whether it does plus 1 or minus 1 we control using this down signal. Okay, so the idea is if down is 0, it should count up, it should do an addition out here. If down is high, it should do a subtraction out here. And we have seen this kind of stuff before. I can always make a circuit which does either plus 1 or minus 1, and then I have this load out here. Now, if you think about this, there are we are guaranteed that up, down, and load are one hot, and reset overrides everything. So what we want to do is, if reset is high, then we want to activate the bottom input. If reset is low and up is high, then I want to activate input number 1. If reset is low and down is high, then also I want to activate this second input. If reset is low and load is high, I want to activate input number 2. And if all of these 4 are low, then I want to activate input number 3. Right? These are the possibilities. So this combinational logic out here is going to do that. It's going to take these signals and it's going to generate the one hot coded select that I have for this multiplexer. So this logic, the way this guy is going to do is, so if you think that the signal out here is a 4-bit signal, so it's a select 3:0, and what this logic is doing is it is generates this signal. So for example, select 0 is going to be 1 if reset equal to 1, and it doesn't matter what the other values are. Select 1 is equal to 1 if reset equal to 0 and up equal to 1 or down equal to 1, and so on and so forth. So you can write down the different cases out here for this combinational logic. So what now there are many other ways you can approach this problem. You can make kind of a single gigantic combinational logic if you wanted, but this is kind of a structured way of thinking about it. If you think about this, this is sort of similar to the way we approached the more complicated combinational systems earlier in the course, where kind of faced with some logic, you break it up into combinational building pieces and kind of design these things. So that's what's happening out here. Question on this? We are going to cover some more examples on Friday, but and the homework, the current problem set does not cover this, so we'll have some more time to look at it. Okay, let's look at one more example. How are we doing time-wise? Okay. Timer module. So there are these hardware things, building blocks that are often available in libraries. They are called timers, and the idea is it's kind of like the timer that you see on your watches and stuff like that, right? I mean, you press a button, it counts up, you press another one, it freezes, you start again. So it's basically used to measure how much time has elapsed. So what we have is a module where there is an input called reset, which resets the timer. It has a load, which loads the timer. What this timer does, it counts down. And when the timer hits 0, it beeps. So it gives a done signal. So essentially what's happening is that we load the timer and then it runs down. When it hits 0, it buzzes. Okay, so it's like our timer in oven or stuff like that, that kind of stuff. So it's used to generate a notification at a future time. So oftentimes in software we use this kind of approach. It basically says, interrupt me or tell me or wake me up 5 seconds from now. Okay, so what under the hood happens is in a timer hardware, we load a counter value, load a value corresponding to 5 seconds. The timer ticks down every clock tick, and when it hits 0, a signal comes to our program saying 5 seconds are up. So that's what's happening. So load a value, let it count, and then wait for done to become 1. So let's see how we can build a system like this. So what would its next state look like? So again, faced with something like this, always think in terms of that using these inputs, I have to define a next state function and an output function. So in this case, it basically says if reset or so if reset is true, next state is 0. If reset is false and there is no load being done, that is load is 0 and done is true, then next state is 1. If reset is false and load is true, then I'm loading the input value. And then finally, otherwise, the next state is state minus 1. So there are basically 3 possibilities. State is decrementing, state is 0, and next state is the input that we have. So we list all of those conditions. And on the output, all we are doing is we are basically saying I have to give out a done signal. So the done signal comes when the state bit is all 0. So we are basically saying that if all the n bits are 0, then the done has come. Okay, so that's basically what is happening out here. So this timer hardware, again, you can imagine building it in terms of a multiplexer. This is how it's going to look like. I will again have a D flip-flop. I will have a magnitude comparator for 0, or basically an AND gate. So that gives me the done signal. I will have a multiplexer. The multiplexer gives me 3 choices: 0 in for current state minus 1. I'll have some logic out here which takes my inputs and the done signal and controls the multiplexer. So all these problems, you're seeing the same pattern again and again, which is state register, a multiplexer, and something controlling the multiplexer. You have to judiciously decide what the inputs of the mux are and come up with Boolean equations for this select logic, and then it's kind of a combination logic problem. Question?
Is there a reason there's a gap in the select logic block?
No, it's probably something to do with my cut and paste or something like that. I don't know. No particular reason. Okay. So again, so we saw timer, we saw counter, we saw that deluxe counter. All of them operated on kind of the same notion. State register, we come up with an equation on what is next state as a function of current state and what is output as a function of current state and inputs. And then we try to map it into a structure like this, where we have a multiplexer and some logic which dictates how the selects are controlled, and usually some arithmetic sitting before the multiplexer. And faced with any given problem, you'll have to kind of do a little bit of analysis and kind of figure it out what is going on as a result. Let's take one final example. I think we still have a little bit of time. In the same pattern, so we want to make a shift register. So what does a shift register do? Shift register has again the property that if reset is asserted, output is 0. Otherwise, on each clock tick, we shift left with the input filling in. There is an input called SIN, S-I-N, which is filling in the LSB. So this is what is going on. I have a single bit input called SIN, and I have a n-bit register. Every clock tick, I shift this register. So MSB gets thrown. Penultimate the bit before MSB becomes the new MSB, and so forth. And I look at this input called SIN, and I put that into the least significant bit position. Okay. So this is what operation does it do? If SIN is 0, and if SIN is 1, then it's multiplied by 2 plus 1. Okay, right? So depends upon what it is. Okay, so again, I can express it in terms of equations. I can say if reset, next state is 0. Otherwise, next state is, and this is this weird notation that sort of the book also uses, so I'm also using it. It's basically saying that the n bits of next state are the the lower n minus 1 bit of state. So bit number 0 through n minus 2, and then comma SIN. So this syntax is basically saying concatenation. Think of it like that. So this is concatenate. Okay, so I'm taking the lower n minus 1 bits, and then to the right of that, I'm putting SIN. That's my new n bit collection, and I'm putting that into next state. What kind of logic would doing this employ? Any ideas? What gates would you use from Logisim library to do this? Just this part. Next state is equal to state n minus 2 colon 0 comma SIN. Huh? It's basically wiring, right? There's no gates. Okay, it's just wiring. So it's actually a pretty simple logic, as you can imagine. And by the way, output is a state. So let's see. This is how it looks like. Multiplexer. One input is 0. The other input is this wiring structure, which you can do with the splitter, basically, in Logisim. And SIN is also feeding into it, and that's it. This is basically our shift left, which is happening. So Again, as you can see, same structure out here. In this case, the logic controlling the select part of mux is very simple. It's just a reset signal, but again follows the same pattern. So again and again, we are seeing the same basic structure. There is a state register, which is where our data value is being held. And I have that new value of the data can have many different choices. And so we put a multiplexer and we put some appropriate combinational logic to make that magic happen. Okay. So we're going to pick this thread up again next week. So again, no lecture on Monday. I'm going to do a makeup for that on Thursday of the following week, so March the 5th. But next Wednesday, I'm going to do a bit of a recap on this, more problems